Hello everyone, this is another video on tensor analysis, and this time we will study tensor calculus. Okay, this will be the last video in the this tensor series, because we have almost covered everything that is required for our study in relativistic quantum mechanics, the things that will be used in relativistic studies from tensor. So yeah, so this will be tensor calculus. Tensor calculus. Okay. So first was is simply is your tensor differentiation. Okay, so I will write covariant and contravariant, covariant and contravariant differential operators. Okay, so I can write del mu is equal to del by del x mu. This is kind of the beginning of relativistic quantum mechanics. Okay, so this can be written as del by del x naught now and del by del x I. Okay, so this is again the zeroth component. These are the first, second, third component. Del zero, and this can be written as delta or Nabla operator. Okay, you know it. Okay, so this is for covariant. We can write it as a contravariant also. Del mu is equal to what? Del by del x mu here. Okay, just to exchange of things is equal to del by del x naught and del by del x I. Okay, you can see a change of indices here. Okay, change of placement and all. And this will be del zero, and this one will be minus. Okay, this will be minus delta. So we have okay. So x naught, have we used the notation, say x naught is equal to eta 0 beta x beta. It can be written as eta 0 0 x 0 is equal to x 0 is equal to ct. Okay, x 0 is equal to always ct, right? So from here we can write that del 0 is equal to what? Del by del x 0 and plus x 0 will put ct. Okay, you can also write this because the zeroth component can be like same covariant, contravariant, both are same. So this is del 0. So I can write it 1 by c, 1 by c del by del t. Okay, because x naught is a ct, so del x 0 will become c del t. Alright, yeah, okay. So like that, xi can be written as what? Xi can be written as eta I beta x beta is equal to eta ij xj, okay, is equal to minus delta ij xj, yeah, is equal to minus xi. Can also write it as like this. So from here we can conclude del I is equal to what? Del by del xi. In place of xi, I can put this. Okay. So minus of del by del xi, and this becomes minus del I. Okay, there is a change of this contrary to. There is a minus sign, and I'm getting this as minus of delta I. Okay. So here delta is simply three gradient vector operator. Okay, the one we know in from simple vector calculus. Okay. Okay, next is covariant gradient. Let's write down. covariant gradient. So covariant gradient we can write del mu phi is equal to del phi by del x mu is equal to then del phi by del x now is not component, zero component, and you're simply del component. Okay, so we can write this as 1 by c del phi by del t is 0. This is a covariant vector, and it gives covariant vector. Right? This covariant gradient now contravariant gradient will be what? The contravariant gradient, contravariant gradient will be what it will be del mu phi is equal to g mu nu geometric tensor del mu phi. Mu cancelled out and it's g d mu, okay, and phi is equal to del phi by del x mu is equal to again 1 by c del phi by del t, and this one will be a minus 2. Okay, for contravariant is always minus, if you see here also it's this one is minus. Now covariant divergence. Covariant divergence. Okay. So del mu a mu is equal to del a mu by del x is equal to del a 0, del a naught, del x naught, yeah, plus del a I, del x I. Right. Right. So again, write it again as this one can be simply del 1 by c. This calculus part is easier than the previous introductory part. You can easily understand this if you have done that properly. Plus, okay, it gives a 4 scalar, okay, and that is a rank of tensor 0. Okay, so you can write 4 scalar of tensor of rank 0. Okay. Suppose divergence of the contravariant tensor. Suppose divergence of a contravariant tensor contravariant tensor supposes T mu nu of rank 2. Okay, how will you write it? Simply del mu T mu nu, okay, contravariant tensor of rank 2 is equal to del T mu nu by del x mu is equal to del T 0 nu divided by del x naught plus del T I nu divided by del x I. Yeah, we can write this as del naught T naught plus del I T I naught, and del naught T naught J plus del I T I J. So we can write like this. Okay. So this again produces a contravariant 4 vector and the contravariant tensor of rank 1. Okay. So maybe we'll say contravariant 4 vector that is a contravariant tensor of rank 1. Okay, contravariant tensor of rank 1. So the operation of divergence giving a contravariant tensor is rank, like it will give a rank of m minus 2, okay, always, because here we took 2 rank and the one we got was rank was 1. Okay. Yeah. So next I have. And next is covariant curve. Covariant curve. Divergence gradient now curve. So curl can be written as C alpha beta. C alpha beta is equal to C alpha beta, like this, square bracket alpha beta is equal to half Lebesgue beta alpha beta mu nu. It's a bit tricky. Del mu a nu minus del mu a nu. Okay. Yeah. A nu, which is equal to Lebesgue beta alpha beta mu nu del mu a nu. Please write it down first. Yeah. Okay. So this gives a what? Contravariant antisymmetric tensor. Okay, this is a contravariant antisymmetric tensor of rank 2. Gives a contravariant antisymmetric tensor rank 2. Okay. Okay, next. Suppose I write the curl. Okay. Suppose I write the curl. It will be something like this: half Levicivita I j k del j a k minus del k a j. So this will be a k del j a k. Right. Okay. So next is your item. The D. This one is most lot we used a lot. The D'Alembertian operator. The D'Alembertian operator. Okay. What is it? So its operator is del square like this is equal to del alpha like this. Okay. So this is kind of equal to del 0 plus del I. Two operators are multiplied here. Del I del I. Okay. So this is 1 by c square d square by dt square minus del square actually. Yeah, this is your del square. You must have studied this in classical mechanics. Okay. Okay. So next write down the 4 volume. Next write down the 4 volume. The 4 volume and tensor integration. The tensor integration. The invariant 4 volume element. The invariant 4 volume element. What is it? Invariant 4 volume element is your dv. Okay. Is equal to what? D fourth x. Yeah. Which can be written as dt into d cube. D3x. Under a transformation, suppose if I write about under transformation, under a coordinate transformation, under a coordinate transformation, what happens is x mu. If I transform x mu to x dash mu, so it will be kind of become what? It will be x dash mu, okay, x dash mu, x naught, x1, x2, and x3, right? Hmm. So the volume element, if this the transformation coordinate, the volume element will transform how? Volume element transforms to volume element transforms to dv dash is equal to what? D fourth x dash, right? So simply it will become del x dash by del x, yeah, and d fourth x, okay. So d fourth x is a dv, so del x dash by del x, and this is a dv, okay, yeah, right. So, so d fourth x is actually a scalar density, okay, tensor of rank 0. Okay. Now taking the determinant, you will see, or doing a bit of like, if you remember this one, I hope you remember the metric tensor. Metric tensor was what? Metric tensor G dash mu nu. is equal to del x alpha by del x dash mu del x beta by del x dash mu g alpha beta. Okay, you see g alpha beta they are cancelled out, so here with the end we will get mu nu because mu nu is downside here, so it will be also in the down part. Okay, so g dash is equal to determinant of what? Determinant of g dash mu nu, correct? So we can write del x by del x dash square and determinant of g alpha. Okay, so we can write it as del x by del x dash square g. Okay, I can write like that. The determinant of this one is simply check. So determinant we can write this as the determinant of a metric tensor is negative in spaces having a like Lorentz transformation and all. So we can write like minus of g dash this is equal to del x, right? And taking root over on both sides, we'll kind of get this. Okay, yeah, yeah. So this is your yeah this one. We can also get like this minus g dash is equal to what dv dash g dash dv dash transformation is equal to minus g, right? dv. This transformation can also be there. So this is your invariant four volume element. Okay, because see, it remains invariant. So this is your invariant four volume element, right? Yeah. So, so in special relativity, we have this G alpha beta identified with the Minkowski what metric tensor, right? Minkowski metric tensor, and metric tensor is what eta alpha beta. Okay. Whereas your G is exactly what determinant of eta alpha beta, which is a minus, isn't it? Yeah. And the invariant four vector element, four volume element is simply what d fourth x is equal to dt and your dqx, which is actually Lorentz gap, right? So these are the important things to remember. We'll use all that, right? Yeah. So yeah, so these are the basic fundamentals of your like we have to remember all this for the use in relativistic concepts, right? They'll be heavily used in relativity, so we have to be really careful about all this. Yeah. Okay. So yeah. So this is your tensor analysis. We have done very well, like all the from the beginning to the like the integration, calculus, differentiation, and all. So I hope you understood, and I hope it will help you in your other chapters. It will really help you, like whether it is relativistic quantum mechanics or relativistic electrodynamics, okay, quantum chromodynamics, all of that. It will really help you. Okay. And I will do also in the next from the next classes we will dive right into relativistic electrodynamics. Okay, that is very important. And on the next class we will do special relativistic particle dynamics. Okay, next class special relativistic particle dynamics. So this is a very important topic again. We will dive into that right away. In that chapter, we will see four momentum, four energy, conservation energy, momentum, all that. Okay, Compton effect and four force, everything with a four current density, like the formulation of electrodynamic equations. Everything we will see the Lorentz force equation. Yeah, covariance of Maxwell's equations. All right, which is very important. Then transformation of electromagnetic fields, scalar invariance, all those things we'll see. Okay. Yeah. Okay. So yeah, that's it for today. We'll see you in the next class. Okay. Thank you.